In this video, I'm going to show you how to use a rotary evaporator, or a rotovap, to remove a volatile solvent from a solution and leave behind whatever is dissolved. So something I haven't really talked about, I will try to interject this into the lab, is the question of what does an organic chemist really do? All right, we obviously study organic materials. We try to purify organic materials. We try to characterize organic materials. And we try to do synthesis where we convert one organic material into another organic material. All right. Almost all of that, in order to manipulate an organic compound, you almost always have to put it in solution. Now, we don't usually use water as a solvent. You know how you've always heard water is a universal solvent? Water is not a universal solvent. It doesn't dissolve organic things. If water was a universal solvent, I wouldn't be sitting here, right? I would be an aqueous solution of various proteins and calcium carbonate and stuff. So we're going to use organic solvents, and we have an advantage here in that organic solvents very often boil at relatively low temperatures. So the way we're going to separate the solvent from whatever is dissolved in it is by distillation. We're going to boil away the solvent, the low boiling solvent. We're going to leave behind a non-volatile compound. All right, so that non-volatile compound could be a liquid that has a very high boiling point. It could be a solid. You can't use a rotovap if the thing you want to isolate boils at a low temperature, right? So if the solvent here, as we got this solution from the filtration video where we used ethyl acetate. Ethyl acetate boils at about 70 degrees C. So, you know, if the thing I want to isolate boils at 85 degrees C, that's a really close, they're close in boiling point. I can't separate them by boiling. All right, so we can't do rotary evaporation with an Erlenmeyer flask, all right? The rotovap, one of the key tricks, I guess, to the rotovap is that we're going to apply a vacuum. All right, when we apply that vacuum, if you put something like this under a strong vacuum, right, the vacuum's not going to apply. Anything with a flat surface is going to be bad for a vacuum, and it will probably implode. So we want to use a round bottom flask. All right, that round bottom flask, when we apply a vacuum, the pressure is evenly distributed. So in the hood, I'm going to pour. You guys feel free to use a funnel. You probably should use a funnel. It occurs to me I should have used a funnel. All right, so I've poured that solution into this round bottom flask, and now I'm going to take it over to the rotovap. So you see here I'm at the hood. I'm simply going to spin slowly. All right, you can see out, look, there's some folks walking along, prospective students. There's a rotovap. Here's the rotovap I've gotten keyed up. So this is the window nearest the door. All right, I'll be right there. You guys probably shouldn't do this. I just need to get my phone and stuff, so I'm going to set the flask there. All right, am I on camera is the question. The answer is yes, I am on camera. All right, so here's the rotovap. This thing that I've got running over here is a chiller. All right, I'll explain what that is in a minute. This is the machine that's going to generate a vacuum for us. So again, I talk in these videos about generalities and specifics. This is our specific rotovap. If you stay in chemistry, you'll experience lots of different kinds of rotovaps. So something that runs cold liquid through a condenser, something that generates a vacuum. This is the rotovap itself. We have a bath of warm water here. Actually, I don't think I've turned the heater on. You don't really need to turn the heater on. The bath is just to replace heat lost by evaporation. Getting ahead of myself. All right. This is we call it a bump trap. That might become important in a minute. We're going to clip the round bottom flask onto this bump trap. So, all right, so you just slide these two ends together. Now, if if I let go, the round bottom is going to fall into the water. So I'm going to use this yellow keck clip, the fat end on the bottom, the thin end on the top. That holds it in place. You see a larger green keck clip there. I'm going to turn the power on here, and I'm going to turn the dial to 30 degrees. 30 degrees is a little bit warmer than room temperature, but not much. And that's going to just heat this water up to 30 degrees. Now, the next thing I'm going to do is turn on my vacuum source, and I am never good with this thing. There's two. You got to turn it on here and there. And then I'm going to hit the, oh, okay. So the vacuum is going to be generated and come through this heavy walled line, the red line. Let's get this a little closer. All right, so the red line here, this heavy wall tubing so it can take a vacuum. Right, this thinner wall tubing, you pull a vacuum through it and it's just going to shrink up. Right, that will allow us to evacuate this entire mess here, right? All the glassware is going to be under vacuum. Again, this is very important that you have your safety glasses on here because this can, I mean, it hasn't in the history that I've been here, but if there's a crack or something, you could end up imploding the glassware. All right, so we're going to pull this whole thing. How I adjust this stopcock tells me whether it's open or closed. And you'll just need to look at this, and I can demonstrate how you would hear it here in a minute. Okay, so it turns. Right now, it's open. There's a little hole in there. It's open again. When the hole is not at this hole, at this tube, or this opening in the glass where it's closed. I'm going to leave it open for now, and I'm going to hit auto on the vacuum. You hear that hiss? All right, it's pulling vacuum, which is creating a sucking sound there. I'm going to close this. And then I'm going to spin the flask. All right. So now, what's going on? How does this help get rid of the ethyl acetate? So we've got a vacuum. What happens to the boiling point of a liquid under vacuum? Boiling point goes down, right? So by pulling a vacuum, I'm lowering the boiling point of the solvent. This is going to let me remove the solvent without heating it up to 70 degrees. And if you look at that, you'll see bubbles starting to form. All right, that's great, you say. Perfect, Dr. Jones. So the solvent's going to boil, be sucked up via the vacuum. Now, we don't want to suck the solvent into our pump, all right? This is kind of a delicate piece of machinery. It's expensive. So you see these coiled lines here? This runs to the cooler, all right? So this chiller is cooling liquid, antifreeze, running through here into the coil, through the coil, out, back to the chiller. So what happens when warm vapor hits cold substance? Well, just think about like your car you come out after a cold night, there's dew on it, right? Maybe ice. So I don't know if you can see it or not. There's starting to be some condensation. We call something like this a condenser. All it's doing is condensing a vapor. Okay, so we reduce the boiling point of the substance by putting it under vacuum. We're going to boil the solvent. Solvent's going to come up here, hit the condenser, and condense and come down here into what's called the collecting flask. All right, so hopefully we collect a whole bunch of solvent here. Now, what happens when a substance evaporates? How does sweat cool you, right? Think about sweat. It's a hot day outside, you start sweating. Why? Well, the way sweat cools you is it evaporates. And when something evaporates, it takes some heat to convert the liquid to a gas. And so the surrounding area becomes cooler. And you can kind of see this in this flask. It's starting to have a little condensation on it because the temperature of the flask, don't ever grab this, but you can kind of put your finger there. It's cold, right? So the temperature of that is going down. So we use the bath to replace the heat lost to evaporation. right? We're not really heating, we're not boiling it. We don't want this bath to be like super hot. We just want it to be warm enough to kind of keep the solvent at its reduced boiling point. Now, I keep hoping we'll see some condensation. This can be a fairly long process. There, okay, so watch the condenser carefully. I know this is like the most exciting TV you've ever seen, right? You can see liquid starting to condense on the condenser. I have no idea how well this is coming off on camera. There you go. There you got some. All right. It's not the most efficient condenser in the world, so it probably is going to miss some. And so back here in the back, we have a second condenser. That second condenser is to just, you know, trap whatever gets past the first condenser, again, to keep the solvent out of your pump. All right, so yeah, I'm never going to win an Academy Award, am I? All right, so let's watch the flask now. Sorry, I keep not tightening the right thing. You guys could probably afford to fast forward at this point if you haven't already. But the solvent is going to evaporate. How do I sound when you're watching this at like 2 times speed? Okay, like I said, the bath is just replacing the heat loss to evaporation. It's starting to condense a little better now. All right, we're getting more solvent there. We're starting to collect some solvent down in the collection flask. You can see some bubbling on in the boiling flask. This bump trap, imagine that we heat it up too much. Say we have something that boil, like dichloromethane, like you guys are going to use in the lab. Well, when I'm filming this in September of 2021, the lab I'm filming it for, we're going to rotovap dichloromethane. Again, you can rotovap anything. All right. This is ethyl acetate. It boils a good bit higher than dichloromethane, so it's boiling smoothly. If this were dichloromethane, though, the boiling point's like 35 degrees C, so it's going to boil super fast. It may explosively boil, and if it does, this trap here will trap it, right? If it kind of boils vigorously, it'll land here and it'll just fall right back down. And that keeps us from losing our material, right? If it bumps, and you almost have to see a bump for you to know what that means. If it bumps, it's not boiling, so it's going to carry the material you want. We're trying to isolate that yellow stuff. So if it bumps and goes all the way up to here, over to the collection flask, then you're just going to lose your material. So that bump trap's important. Why are we spinning it? Well, by spinning it, you increase the effective surface area of the solution. And you guys should think about this, like when something boils, it's liquid, molecules in the liquid state escaping to the gas state. To do that, they have to be at the air-liquid interface. And the more air-liquid interface you have, the faster the evaporation. So you can do this at home. This would be a cool experiment for you to do. Impress your art history friends. Take a really, take a really narrow-necked bottle, fill it up with put 100 mils of water in it, and up to the neck so that the water's in the neck, and then take like a really wide jar and put 100 mils of water in that so that there's a big top, and then follow it and see which one evaporates fastest. Like I said, I know how to party in a dorm room. All right. So you can see some solids starting to come up, right? We've evaporated enough solvent now that solid is starting to come out of solution. And again, we're like 5 minutes into this. So rotovapping is not a fast process. Distillation is not a fast process. And in fact, in almost any purification technique, the slower you go, the better your separation will be, the better your purification will be. So when there's 40 of you in the teaching lab and it's a beautiful afternoon, which it is outside. I mean, look at this. Geez, I hope you guys, it's Friday afternoon. I hope you guys are doing something more fun than watching a rotovap. Okay, but we're going to be in a hurry. Everybody's going to want to go home. Your TAs, me, you, everybody wants to go home. But if you rush this, solvent bumps, you have to do it again. Or maybe you don't get rid of all of the solvent. Maybe you don't wait long enough and you pull some of your solvent into your pump and you damage your pump. So you always in the lab want to go slowly. Like, don't poke around. Don't not study. Be prepared. Know what you're doing next, but think through everything. Every action before you do it, think about it. I'm going to do this. Why am I doing this? And that way you will be a lot safer. And screwing up, doing something right slowly is always faster than doing something fast and screwing up and having to do it again. Like I said, I hope you guys have been watching this. It's fun to watch the solid come out. Like, that's really cool, right? Now, are we done? What I would recommend, certainly in a research lab, like, it looks like we're done. If you look at this really closely, got to make sure I don't drop my microphone in the water, right? That looks like there is no more solid in there, or sorry, no more solvent in there. There almost certainly is. And so what I would recommend is just leave it for another couple of minutes. I always do this. Once you think it's done, leave it for a couple of minutes. In a research lab, the next step to this would be to apply what we call a high vacuum. So right now, right, we're at about 130, about 140 torr. Right, that's not a real high vacuum. It's certainly, you'll feel that suction, but it's not super high. We have vacuum pumps, basically just a little motor that you hook the exhaust up to the flask, where we can evacuate that flask down to a millitorr, and then that will sort of pull off the last remaining vestige of solvent. Okay, I'm going to call this good. So how do we then reverse this? What's the steps to reverse it? All right, the first thing you want to do, open up the stopcock, release the vacuum. All right, you never want to shut the pump off before releasing the vacuum. And in fact, I'm going to kind of cheat and pull this out all the way. And now I'm just going to turn this off. When you do this in the lab, don't turn this off, all right? A TA or me will help you with the rotovap. We won't turn this machine off until the end of the day. But let's assume you're doing this in a research lab. You want to turn all this off after you've released the vacuum. Because again, if you shut this down with this still under vacuum, you're going to have competing vacuums and you can damage the equipment. Now, the next thing is stop the spinning. You can turn that off. There's a little, you'll see this when you come in, there's a little lever here so we can lift this up. Hold on to the flask. This is your valuable product. You've worked all day, or maybe you've worked for 6 months to make this yellow stuff. Pull this keck clip off, not holding on to it, and it falls into the water, and you start all over. All right, so pull the keck clip off, pull that off. Now, hopefully you've weighed this flask already, and you can go weigh it. Right, if I know the weight of the flask, I can weigh the two together and I know how much solid is in there. So before you rotovap, always weigh the flask. But anyway, look at that. Isn't that cool? Yellow solid. It was a yellow solution, now it's a yellow solid. All right, turn the bath temperature off. Everything's off here. It didn't bump, so I don't need to clean this. It's a good idea in a research lab, if you're ever there, always clean the bump trap before you rotovap. All right, somebody else, not everything is yellow. So somebody could have left a colorless impurity here. You don't see it, you put your flask on there, and now your material has that impurity in it. All right, I'm gonna turn the chiller off, and I'll run through this one more time, all right? The general layout of the rotovap. All right, so we've got a chiller. That's gonna power our condenser, right? So our condenser is gonna be at a very low temperature so that the vapor that hits it condenses. Condenser, it's gonna condense gases. Bump trap, this is where we put the collection flask, all right? So we'd have this here. We'd spin it. By spinning it, you increase the surface area of the solution and you facilitate evaporation. We have a warm bath. Again, this can supply heat to either drive evaporation or to replace the heat loss due to evaporation. We have a collection flask. The vapor that hits the condenser falls down here. And most importantly, we have this vacuum source. And again, it could be any vacuum source in reality. So we have this vacuum source that's going to evacuate this entire area that's got your solution in it, and that's going to effectively lower the boiling point of the solvent, right? And so this never got above 30 degrees C, and yet we evaporated a solvent that boils at 70 degrees C. Pretty slick, huh? So if this yellow material were something that were heat sensitive, like maybe it decomposes at 50 degrees, it's still fine. All right, so lower the boiling point of the solvent by vacuum, spin the solution to increase the surface area of the solvent, and supply a little bit of heat to replace that loss due to evaporation or to get it up to the boiling point. And then make sure you've got a condenser that can condense the vapor so you can collect, right? We collected our ethyl acetate there. Hopefully you can see that. You can recycle that or you can dispose of it in the organic waste, but most importantly, it didn't get into our vacuum source. All right, that's the rotovap.